Today we will talk about factor analysis using principal component rotations. We'll start just with a discussion of factor analysis. What is it? Well, it's a lot. It's the art of extracting latent, which means hidden, variables from data. Now, there are two types of factor analysis. The first is the one that we will most likely deal with. This is exploratory factor analysis. And that's when we find those factors without any a priori hypothesis, which means we're not looking to confirm that a hypothesis is true in our data. We're just looking for hidden patterns. Whereas in confirmatory factor analysis, which is integral to survey design, this is where you have designed a survey to measure a certain set of factors, and you want to confirm that your survey does indeed measure the things that it was designed to measure. Now, the example we're going to work through today, we're going to pretend that it's exploratory factor analysis, but you can easily see that it's a survey and we are really doing something more closely aligned with confirmatory factor analysis. But the reason why I'm using the example we use today is because it really shows what PCA rotations can do for interpretability. How is factor analysis different from PCA? This is a question I get from students every year. And the answer is, well, it's not. Principal components is actually a method for factor analysis. There are other methods like maximum likelihood estimation, and all of those are beyond our scope. We are just going to scratch the surface of factor analysis and talk about how, like, kind of this area of overlap here, where we can use principal components for factor analysis. It's a very common technique for it. So when is principal components inside factor analysis and when is it not? Well, principal components has a lot of applications. It can be used to reduce the dimensionality of our data. We can use that to input into a clustering method or into a predictive model, as we'll see soon. We can also use it to explore collinearity in our variables, because principal components is going to show us the collinearity structure. It'll show us the variables that all kind of cluster together. But we can also use principal components to find latent features. And when we do that, that is when we are existing in the realm of factor analysis. I want you to recall this example from our first day of class, where we had some text. We put it in a term document matrix. We had two documents that were about pets, two documents that were about injuries. And when we got this matrix factorization, which was not principal components, by the way, so don't expect this to look anything like principal components. What we got out were these two factors, and we used these two factors to interpret what our documents were about. And we said, you know, factor one was mostly about pets, factor two looked like it was more about injuries. Now, what made this so easy for us to interpret? Well, we looked at the loadings, right, on each factor, and they were very clear in telling us a story. But that clarity was brought to us by sparsity. Sparsity is just having a bunch of zeros, essentially, right? It was having these zeros and the other numbers in the factor being relatively large compared to zero that allowed us to interpret what this factor meant. If I put a 0.8 here in factor one, a 0.9 here, and a 1.2 here, suddenly you would look at factor one and you wouldn't really have a defining term for it. I mean, it would be maybe injured pets, right? All the words would contribute to factor one, making that interpretability very difficult. And that's often where we find ourselves in principal components. We find that all the variables have some non-zero loading on all the principal components, and interpretability is very challenging. So what we're going to do is try to encourage that sparsity. And we do that through rotations of our components. Okay, so we can actually achieve a more sparse loading matrix by rotating our principal component axes to line up with our original variables. Now, we do this after we've reduced the dimensionality of our data. So here on the left, I have our biplot from the UK food data set, right? I have already projected this data into 2 dimensions, okay? So here, the rank of my approximation is 2. I've projected the data down into 2 dimensions. And now, looking at this picture, the problem I'm gonna solve is that, you know, I want principal component 1 and principal component 2 to more closely align with a certain group of variables. Now you can see, once I do this rotation, I have this kind of group of confectionery, alcoholic drinks, and cheese, all much more closely aligned with my second axis. And this group of vegetables, along with sugar and beverages, are much more closely aligned with my first axis. All that's happened to get from point A to point B here is I've rotated this picture, right? Everything is proportionally the same in both pictures. I've just rotated the entire image in the second one so that now I can say things like, you know, as you go along the second axis, confectionery, alcoholic beverages, and cheese increases, right? Principal component 2 is more closely aligned with this group of variables. I should say axis 2. And axis 1 is more closely aligned with this vegetable group of variables. Now, these are no longer principal components. They're rotated components. No longer does this first axis explain the most amount of variability. And no longer does the second axis explain the most amount of variability orthogonal to the first. But together, they still capture the same amount of variance that they did over here because I haven't changed anything. I've just rotated the picture. So once that number of components is decided, we can rotate the axes so that they more closely line up with groups of original variables. It does not change the total amount of variance that's explained by all of those factors together. It only changes the proportion of the variance that's explained by each factor. And the goal, the reason that we do this, is to make the solution more interpretable. How? By making the loadings more sparse. We're going to see this in action with this personality test data set. And the result of the rotation in this data set should be very clear and very convincing that it will help us get these latent factors that are interpretable. This personality test is designed to measure 5 latent features of personality. The first is agreeableness. And there are 10 questions that ask about agreeableness. Now you can see some of these, like, I feel little concern for others and I insult people, really measure disagreeability, right? But this is how social scientists take measurements, is they ask both ends of the spectrum about disagreeableness and agreeableness. Should read those. The second is conscientiousness, okay? And you'll see the same thing here. Question 1, I am always prepared. Question 4, I make a mess of things, right? We expect someone who's conscientious to score highly on question 1 and not highly on question 4. The next one is extroversion. So again, I'm the life of the party. I don't talk a lot. These things are anti-correlated. They're negatively correlated. The next is neuroticism. So I get stressed out easily. I worry about things. Kind of measuring a mental health kind of angle about mood swings, emotional stability, perhaps. And the last is openness, is what they titled this. You know, talking about imagination and ideas and reflection. There's some additional variables in this data set that we may choose to use. I apologize for the formatting on this slide. I just copy and pasted it from the data dictionary, but we have race, age, English national, so whether or not English is your, or English native, whether or not English is your native language, gender, handedness, be right-handed or left-handed or ambidextrous. And then we also have a country code. Now, we are gonna use ProcFactor to do this analysis. And ProcFactor, the default version of this, is no different mathematically from ProcPrinCom. The only difference is that SAS scales those principal component columns by the standard deviations. So it's just a scalar multiple of the output from ProcPrinCom. That first factor we'll get as output is precisely the same direction as the first principal component. So we can get into SAS Viya and you can follow along there. But if we run this code where we put in the IP data set and we specify the variables E1 through O10, those are all the questions, just the questions that we looked at. The output that we see, the first thing, it says right at the top, initial factor method, principal components. It gives you first the eigenvalues of the correlation matrix. Okay, so by default, it's using correlation PCA. And below that, it says 8 factors will be retained by the min eigen criterion. This min eigen criterion, also known as Kaiser rule, is the default for choosing the number of factors. And what it does is it chooses factors that have an eigenvalue greater or equal to 1. So on the last slide down here, you see there were 8 eigenvalues greater than 1. So it chose to cut off all the factors after 8. Now, what's the motivation for this? Well, we're using correlation PCA, which means our data is standardized, which means each variable has a variance of 1. So we only want components or factors that have variance that's at least as big as our original variables. Now, the next thing we're going to do is we are going to actually specify the number of factors to be 5, because 5 latent constructs are what we're trying to extract. Right? And this is why this is more like confirmatory analysis, because we have this hypothesis that we can measure extroversion, openness, agreeableness, etc. Okay, so I'm going to go ahead and specify the number of factors to be 5. Once I do that, I am given the variance explained by each factor, and I can go ahead and note that that will be the same as the eigenvalues of the correlation matrix, as expected. And then in factor analysis, it's also common sometimes to talk about communalities. And communalities tell us how much of the variance in each individual variable, original question, is explained by our factor model. So it's, in a sense, it's how well is the information from this question captured if we reduce the dimensionality down to these 5 factors. Okay, and some are better than others. So here I have a 0.64 commonality. So that means that 64% of the variability in question A4 can be explained just by using this reduced dimensionality 5-dimensional data. Now, you can actually think of this as the R-squared of predicting each variable by the factors determined by the model. So I can demonstrate this on the next slide here. If I actually output those factors into an output data set, I specify 5 factors, I can get the communality from that table. For E1, it was 0.514. If I actually run a proc reg predicting question E1, so I'm going to try to predict this question from factors 1 through 5, you'll see that R squared is precisely that commonality. Okay, so it really is. How well can we explain the variability in E1 using these factors, these 5 factors? All right, now let's move on to the factor pattern. Now, these are the eigenvectors. They are scaled by square roots of the eigenvalues. That's irrelevant. They're scaled by a constant, okay? These are the eigenvectors, essentially, from principal components. I have 5 of them. If I look down the loadings, so this is the first set of loadings for questions on extroversion, neuroticism, and then I have agreeableness, conscientiousness. Now it does look like these numbers have dipped off a little bit on this slide. I'm only looking at this first factor. These numbers have dipped off a little bit from these. So they're a little bigger. But as I click through to the final bit of this column, I see these factors are just not so easy to interpret. So the solution here is rotation. There are 2 common rotations for factor analysis. The first is Varimax, and this is to simplify, the goal here is to simplify the columns of the factor matrix so that each factor has only a few variables with large loadings. Now, when I talk about the factor matrix, I'm saying this big list of numbers, right? In every column here, I'm going to try to simplify it so that it has mostly zeros and just a few variables with large entries. The next type of rotation is Quartimax. Now, these two procedures have separate goals, but the goals are kind of achieved simultaneously, okay? Because in both cases, we're trying to create fewer loadings, fewer non-zero loadings. So Quartimax operates along the rows and tries to make it so that each variable will only load on a few factors. So looking at this matrix, it would try to make only a few of the entries in each row be non-zero. Again, if I solve for Varimax, I'm going to get something that looks pretty good in terms of Quartimax. And simultaneously, if I do Quartimax, it's going to look pretty good in terms of the Varimax goal. We're going to start with Varimax. It's really the most common of the 2. So now I have proc factor. Again, parenthetical, not really any different from proc print comp, except that it has this option to rotate. So that's why we're using it. I specify the number of factors. I'm going to specify a rotation. I'm going to ask for the output of scores. And again, specify I want all the question data going in. When I look at the rotated factor pattern now, I see exactly what I want to see. I see that all the extroversion questions are loading up on the first factor. All of the neuroticism questions are loading on the second factor. Now, again, the other entries in this vector are not 0, but they do now pale in comparison to those that are highlighted. Next, I have agreeableness on factor 3, conscientiousness on factor 4, and openness on factor 5. So now I have these 5 new variables, these latent variables. Factor 1 is a variable for extroversion. Factor 2, a variable for neuroticism. Factor 3 for agreeableness, 4 for conscientiousness, and 5 for openness. Now, I want to address there are some negative elements in here, and that's just for the questions that are, again, anti-correlated with the overall construct. So here we're looking at openness. I have a rich vocabulary. Apparently, that's what someone who's very open would say. The next, I have difficulty understanding abstract ideas. So someone who is more open, right, who has a higher score on factor 5, should have a more negative score on this question, right? Because they would not be as likely to say this. So you get this mix of positive and negative questions, and that just shows, you know, what you expect from someone with a high score on that factor. So here I can actually use these factors in a model. So I can explore things like gender and handedness by using these constructs. So here I'm actually creating new variables, one for female and one for whether or not you're a lefty. And there's a question you can ask: are females more agreeable, proclogistic, right? I'm just predicting whether or not someone identified as a female by factor 3. That was the agreeableness factor. Yep, we are. And, you know, there's a lot of discussion about this in social science literature and at my extended family dining room table. And I think that there are, you know, evolutionary arguments for why this may be true. Females learning to survive perhaps more aggressive ends of the species by being more agreeable. Now, what else can we say about females versus non-females? Well, it actually turns out there are differences between genders along all of these constructs. Some of them smaller than others, the largest being agreeableness, the next being neuroticism. Females more likely than non-females to identify with some level of neuroticism. Openness, actually less likely to identify with those questions of openness. More likely to be extroverted, more likely to be conscientious. Again, these chi-squared statistics are quite small. P-values also, or p-values are still quite significant. Now, are lefties more neurotic? Nah. Are there any differences for handedness? Well, actually, kind of. This is a lot of data for accepting that level of p-value, but it gets close. Openness gets close to showing differences between lefties and righties. So thought that was interesting.